All right. Hey, everyone. Welcome to, this is my last lecture of the semester. Pretty crazy. Last lecture of the year. Maybe last lecture of the pandemic. We'll see. I'm not scheduled to teach again until August 2021, so we'll see what kind of world we live in then. Hopefully a better one. We'll see, but thank you for joining on the today's December 10th. We do have one more lecture next week. It's going to be with a guest lecturer, Thomas from Instagram, so that should be pretty interesting. So I hope you're all having a good week. Let me go ahead and turn it over real quick. So Arvind and Rohan, any announcements?
I just wanted to say this that we have created a new Zoom link on Canvas for the final presentation for the groups who do not have a industrial partner. So just please hop onto that meeting and give your final presentation.
Great, excellent. All right. Okay. Anything else, guys?
Just one more thing, so that students know they have an assignment created where they can go ahead and submit their recorded presentations with the industry partners.
You broke up a little bit for me, Arvind. Were you able to hear Rohan okay?
Am I audible now?
I'm not sure if it's my connection.
No.
Hernan says voice was poppy. I couldn't quite hear what Rohan said. Yeah, okay. It seems like the class couldn't quite hear. Rohan, do you want to try one more time? And if that doesn't work, maybe you can chat the announcement.
Am I audible now, Professor?
Yeah, that sounds really good. Yeah, go ahead. Just repeat your announcement, please.
Just so that students know, there's one assignment created where students, groups with industrial partners can go ahead and submit their presentations with the industrial partners.
Great, excellent, thank you. Okay, perfect. All right, anything else, guys?
No,
That's
Professor.
Okay, great. Alrighty. And yeah, so you have, how many grades do you have left? I think it's just three, yeah. So let me do a screen share real quick. All right, hopefully the internet is kind to us this week. This has been a weird week. I feel like internet's having issues. Microsoft Teams had issues earlier this week. Just weird stuff is kind of happening. The models I was training this week for work didn't do very well. It's just one of those weeks, you know. So here we are. So just a reminder, on Monday night, you have the Module 6 Programming Challenge. And that is, we're excited to see what you submit here. So again, just as a reminder, you are doing a 3D reconstruction of something. And you're not required to write any source code. So you're just using this library. So you're using this library called OpenSFM, and you're creating your own 3D reconstruction video. You can pick whatever you want. It can be a building, it can be your room, it could be a house, and you're going to run it through OpenSFM. There are some details, you know, it's easiest to run on Linux, so you may want to use a virtual machine, or if you have a Linux machine, I'd recommend you use that. You can run this on Mac, but it's pretty hairy, so I recommend running this on Linux. Let us know if you have any questions about it. But the biggest part of this assignment is just taking good images, so you can have a good reconstruction. Not all images will work. Yeah, Hernan, great question. You do not need a GPU. I don't believe OpenSFM has any kind of GPU optimization, so it won't benefit you at all. And OpenSFM can be a little slow. This reconstruction might have taken an hour or something, I think, although I can't quite remember, but it could be a little slow, but GPU won't help you. So, great question. But you may take a first set of images and OpenSFM, so do a little bit early. But this is not designed to be a terribly difficult challenge. It should be a little creative. I'd say it's not terribly difficult, but it can be a little time consuming because you need to take a series of images with your group to run open configuration file, this config.yaml, and actually let me go ahead and open this. Let's see, do I have a link to it? Oops. Hopefully I have a link to it. Let's see. Yeah, okay, cool. All right, so let's see, where does this link? Oh, that's nice, yep. Not found. They must have moved this. Let's see here, is OpenSFM still where we thought it was? Yep, it's here, good, okay. They must have moved the config location. Let's see if we can find it real quick. Because I just want to look at the config with you guys real quick. Oh, did they make it into a PI file? That's funny. I prefer YAML, okay. Oh yeah, looks like it's a PI file, okay, cool. So let's just look at this together for a minute, because what you'll see as you're working on your challenge, your programming challenge, which really here, there's no programming required, just changing this config file and running OpenSFM, but let's just talk for a minute. So if OpenSFM doesn't work for you the first time, which often it won't, it's not a perfect library, you can either go back and take more or different pictures, or you can play with the configuration file. I'd recommend the config a little bit, just to see if you get better results. And just to talk you through a few things, so I think you might be aware of what's going on here. So look at this. So you get to pick the feature type. So notice there's different feature types. One of the features, at least one of these or two of these you should have heard of, right? So I hope you've heard of SIFT at this point and ORB. So if you want to try SIFT instead of, this is called HeyHog, Hogs for histogram of gradients. I think Hey is Hessian or something. I don't remember, but you can try to detect more features, for example. I think that's, let's see, min feature, yeah. So you can increase the number of points you detect, which it'll be slower, but you may get a better result. You can play with different thresholds, things like that. There's going to be information in the documentation that may help you choose these features a little bit better. But there's a bunch of things to play with. So OpenSFM may, and like I said, if it works perfectly out of the box, that's fine. You can submit that. But if it doesn't and you want to get better results, then you can play with the config file, or you can get different images, or you can try both. So those are really your options. So I'd say what makes this assignment, it's not hard, but what makes it take some time is first you need to capture a set of images. And you may have to do that more than once if it doesn't work the first time. Then you need to set up your computing environment, which we recommend Linux. So you can use a virtual machine, or if you have Linux set up already, you can use that. And you only need one per group. So you can use Azure credits. There's a way to get $100 of credits for students. And just chat us or post on Piazza if you have any issues. But the first thing is setting up your environment, getting images, running OpenSFM, see how you do, and then make any changes that you need to get a nice visualization. Yeah, so how many images would we recommend? So in this reconstruction, I have used like 30, something like that. So you can use as many as you'd like. It's going to get slower as you get more. I would recommend at least 20. You may be able to get away with 10, but I wouldn't try like 3. I've used 30 here. It depends on how complicated the thing you're trying to construct is. You know, you may want to get ambitious and do like a building. Then you might want 100 or something, but it will be slower. So at least 10, you know, I'd probably recommend 30, something like that to start with. Great. If there's any questions about the challenge, please throw them in the chat window. Arvind and Rohan, anything else to add about that? You guys didn't actually do this challenge, Arvind and Rohan, because we skipped this module last time, so you guys have not had the pleasure of doing this. Anything to add to this, Arvind or Rohan?
No, Professor.
No.
All right, great. Okay, cool. But yeah, so Austin says we want a whole 360. So it's interesting, if you look at this 3D reconstruction that I've made, and it'd be cool to show you guys a live demo, but I just didn't have time to put that together for you this year. But if you can see where the cameras are, those are all the cameras are, right? And it's one camera, it's just moving. You can see where they all are. Now, I didn't go all the way around, right? So if I turned this model around and looked beneath it, for example, it's actually hollow. There's no backside, right? And it's because I didn't take pictures all the way around. So it's up to you. The main thing that we're really shooting for, and what we're going to be kind of grading you on, it really comes down to the aesthetic. So does it look good, you know? And it doesn't have to look perfect. Like this is like, as far as like quality of appearance, I would give this like an 8 out of 10. What I did here, and if yours looked this good, you receive full marks. Yeah, so Ashish is having some trouble on Mac. Yeah, I barely got this working on Mac, Ashish. It was hard though. I would really recommend using a Linux VM or something. You can get it to work on Mac, but it's difficult. So you may want to try Linux. Let's see here. So Monica says, so the instructions given in the challenge GitHub page are to run OpenSFM. That's right, Monica. Yeah. So the challenge page, it walks you through. Here's your instructions, and really I'm pointing you towards the README of OpenSFM. That's where most of the instructions are going to be for running it. So here's OpenSFM. Here's the instructions for how to run it and stuff. I think there's a getting started, building the library, running a reconstruction. So the documentation is really inside of OpenSFM, but in here I kind of just walk you through the high level stuff of what to do. But yeah, it's in the README for the challenge. And then I tell you about different, and actually what we don't have here, Arvind and Rohan, is I recommend Amazon EC2 as an option. But we also, so Microsoft Azure is also an option, and we have as part of your project, we have Arvind has a nice write-up about how to get some free Azure credits for students. So what we don't have in this list is Azure. Arvind, would you mind taking a note, Arvind or Rohan, just to add a little note here that links to that page you made about the Azure credits?
Okay. Sure, Professor.
Thank you so much. Okay, awesome. Okay, great. If there's any other questions about this challenge, please throw them in the chat window. If not, we will get into today's lecture. We're looking forward to your reconstructions. This is a pretty fun thing to do, I think. I hope you enjoy it. And hopefully it'll tie together a lot of the concepts that we're covering in this module. But you only have, like I said, just a few grades left. You've got your final project submissions next Wednesday. And then we've got, on next Monday, you have your last quiz, and then your Module 6 programming challenge, which is the reconstruction. Okay, for the last quiz, again, it's just going over the lecture notes. The kinds of questions I ask you in lecture are very much the kinds of things that'll be on the quiz. As always, there shouldn't be any surprises. We're not trying to trick you in this class, nothing like that. Great, so it's 2:41. We've got about an hour of class time left. So let's go ahead and hop into a lecture. We'll talk for a while, and then maybe we'll pause and kind of, this is my last lecture, so maybe we'll kind of chat about the overall class a little bit. But first, I'll go ahead and hop into this lecture. So what I really want to do in this last lecture, and there will be a little bit of it on the quiz, I would like to get you a little more comfortable with this equation. So some of you, maybe this equation, you feel good about it. Some folks may be struggling a little bit. If you're familiar with three-dimensional linear algebra and this kind of thing, it might be easy. If you're not, it can be a little daunting. It's a little bit of there's a lot of variables in here. This is not high school mathematics. This is definitely college level mathematics. So I'd like to really make this hopefully very tangible for you by solving a real problem, actually 3 real problems. And in the process, we will develop some models of transformation as promised by the title of the lecture. But really what I'm trying to do is, what I've done, and we'll get into this in more detail, but I've drawn some points in world space, right? So here's some real points on a plane in world space. And what I'm kind of saying to you is, hey, let's let this be the origin, right? So here's U, here's V, W would be coming out of the plane, for example, or we might do into the plane, I can't remember, but here's a real point, right? Here's a real point at 50, 50. I really measured it. It's actually in millimeters. It's like a physical world thing. And remember that, the whole point of this equation is mapping world coordinates to image coordinates, and then possibly going backwards in some cases. And, if this equation really works, then I should be able to solve it and actually, be able to compute where this point should end up in pixel space. And it should actually kind of match what we see in the image. Let me back up a little bit. So that's really what we're about to do in this lecture, is for a series of images, we're going to find points in world space, and we're going to figure out all of our constants in that big long equation. And it's going to spit out an XY location, right, in image space. And we're going to plot it, and we're going to cross our fingers, and we're going to hope that the projection, that the point that the math turns out, we hope it's right here, or very close to right here, because that's where this point showed up in the image. We have the luxury as humans, I can look at the image and I can say, oh, there's the point, right? It's at location 500, something, and at 1500 or something, right? I can look and I can see it. But we're about to do the math, that should describe that process of actually mapping from the world to the image, and we're gonna see if it works. We're gonna really test it and walk through it. So let's get into it. So first of all, the intrinsic matrix. If you remember last lecture, we calibrated our camera, and we determined this intrinsic matrix. So this is our focal length parameters. This is our X offset parameter. This is our Y offset parameter. So we have this. This was determined by camera calibration. If you're confused at all about that, please go back to the previous lecture. We'll talk through camera calibration. We haven't really talked about extrinsics very much, and I really hope this lecture helps you understand extrinsics. So we'll get into that shortly. So this is our intrinsic matrix. I'll run this cell, and again, here's our pinhole camera model of the world, and here's our coordinate system. So let's start getting into more detail here, because I want to plug in some more numbers. Is what I'd like to do, really. So let's get into that. I went ahead and I measured this distance. So the distance from this plane to the optical center of the camera is 310 millimeters. 310 millimeters. So what I want to do then, I want to get you thinking a little bit. So here's the extrinsic matrix, right? So it's right here, and let's see, am I going to give anything away? No, not really. Okay. So here's the extrinsic matrix, right? And again, the idea is that the extrinsic matrix, it captures the orientation of your camera relative, and I should say orientation and location of your camera relative to your world coordinate frame, your world coordinate system. In this case, I've decided that the world coordinate system, and I've just made a decision, right? I've decided that its origin is right here, right? The origin is right there. That's the origin of our world coordinate system. And I've defined V as down and U as to the right. And W, I believe I've defined it positive upward. It might be positive downward, but I believe it's positive upward. We'll have a closer look in a minute. But this is the coordinate system I would like to use. That's the idea. That's what I'd like to use. And given the location of the camera, it's pointing straight down, right? It's pointing straight down at the image, sorry, not at the image, at the piece of paper, right, at the plane. And it's 310 millimeters above. So based on those facts that I just told you in words, where the camera is relative to the origin, relative to the ground. Camera's up here. You should, well, I shouldn't say should, but I'll say this. We now have enough information to uniquely determine all 12 of these variables, all 12 of them, right? That might sound like a lot, but everything I've just told you, that's enough. It's enough to know exactly what the values are for all 12 of these, which might seem kind of far-fetched, but let's start to talk through it. So let's ignore the omegas for a second. Let's talk about the taus. So tau 1, tau 2, tau 3. Does anyone remember what roles do those play? What does tau 1, tau 2, and tau 3? What do these represent about our setup? Please throw it in the chat window if you know. What kind of values would we expect for tau 2, tau 1, and tau 3? And what do they represent? What do those variables represent in our extrinsic equation? Yeah, so Hernan says the pose. Yeah, so it's part of the pose. The pose includes one other thing, but yeah, so that's a fine answer. It's sure. What do they represent individually? Like, what's the difference between tau 1 and tau 2? Any ideas? Okay, no answers yet. That's okay. Let me slow down a little bit. So let me go back up to this equation. So here's the equation again, the overall equation. And this is the extrinsics. And my definition here, I say that this rotates and translates world coordinates W into the reference frame of the camera. So really, these variables, these 12 numbers, they're supposed to describe like where the camera is and which way it's pointing relative to the world coordinate frame. And the omegas, these are all about rotation. And the taus are all about displacement. They're about just moving in a direction. And they correspond to the 3 dimensions that we've set up for ourselves. So tau 1 represents displacement of the camera relative to the world coordinate system in the U direction. Tau 2 corresponds to the V direction. And tau 3 corresponds to the W direction. And remember that U is to the right in our coordinate system, V is down, and W is down the length of the camera. And just one more picture to show you. I've mirrored that here. So V is down, right? U is to the right. Because, well, yeah, let me back up a little bit. So let me say this in words carefully one more time. So what tau 1 represents, it is the displacement, the motion, the movement, or I shouldn't say movement. It's the displacement's really the right word. You could say location maybe. Tau 1 is the displacement of the camera relative to the world coordinate system in the U direction. So U is left and right, right? U is left and right. So if I look at this picture, for example, right, you can see that I've set up the camera so it's directly above the origin of my world coordinate system. The origin is here, and the camera is directly above. So that information alone actually tells you what U is. Any guess? What is U? What is the displacement of the camera relative to the world coordinate system, and here's the origin of the world coordinate system, what is the displacement of the camera relative to the world coordinate system in the u direction? Any ideas? You guys are quiet today. I know it's the end of the semester. You're probably losing a little bit of energy. I'll give you a hint here. So if the camera had been moved, let's say 100 millimeters to the right, then u, or the tau 1, would be 100. It represents how far the camera is moved left or right from the center of the coordinate system. So because the camera is directly above the origin, the u is 0, or tau 1 is 0, because it's not moved left or right. So tau 1 is 0. Tau 2, now this one's a easy question. So someone will get this right. What about tau 2? So tau 2 is the displacement in the v direction, right? So it's the position of the camera above the origin, and if it's moved this way or this way, basically up or down relative to the origin, what would be the value of tau 2? Yeah, thank you, Ashish. You guys are alive. Good. You guys haven't all died. Good. So it's 0. Great. Cool. Okay. So we have tau 1. We have tau 2. They're both 0. While we're on this, actually, let me go to this picture now, though. This will kind of help us think about tau 3. What is tau 3? What is the displacement of our camera in the w direction? It's the height. Yep. And in this case, it's 310 millimeters, right? So that's tau 3. So that's what I was trying to really get you at for this. So those are the first 3 things I want you to know. So tau 1 is 0 because the displacement of the camera relative to the origin in the lateral direction is 0 because it's right above the origin. And tau 2 is also 0 because the camera isn't moved up or down relative to the origin. And then tau 3 is the height, the vertical displacement, and that's 310 millimeters. So this goes 0, 0, 310, which we'll plug in a second. Okay. Let's talk about all this mess. So all of these omegas, right? So what did we say these represent? So if tau 1, tau 2, and tau 3 describe the displacement of the camera, what did the omegas describe? What did those tell us about our camera? If it's not displacement, what do they tell us? What did they measure? Any ideas? What do we need to know about our camera besides its location, right? So I know where it is in space. Yeah, it's the rotation, right? Thank you, Hernan. Because if the camera, right, if this math is supposed to describe exactly what a camera will see, basically, right? So it's not enough just to know that the camera's here, because the camera could be here but pointing upward, right? And if it was pointing upward, right, that'd be you'd see something different. So the rotation describes which way the camera is looking in 3D space. Now, notice that there are 9 numbers, omega 1, 1, omega 1, 2. There's 9 numbers we're using to describe rotation. And depending on your background, you may have heard of an idea called the degrees of freedom. Degrees of freedom. If you've done any kind of physics, you've probably heard of degrees of freedom. And it comes up in computer science as well, I believe, in some domains. But the idea here is that yes, there's 9 numbers, but there's actually not 9 like degrees of freedom. There's not like 9 dimensions I can turn a camera in. Really, there's 3, and if you use something called quaternions, there's 4. But the camera is not. This is we're basically. If you know, like, there's this idea called Euler's angles, and I won't get into it into too much detail, but like, how many numbers do I need to describe like where a camera is pointing? Really, it's 3. So I need to know. It's called, often we call it roll, pitch, and yaw. So the roll is which way is the camera angled, like this. The pitch is this direction, and the yaw, Y-A-W, is this direction. So we've got roll, we have pitch, and we have yaw, right? So with those 3 numbers, the Euler angles, you can describe where a camera is. What we normally do, though, to make the math easier is we actually turn that into what's called a rotation matrix. That's why you have 9 numbers. And those 9 numbers only have 3 degrees of freedom. If that makes sense, great. If not, don't worry about it. But these 9 numbers, they let you map from one rotation to another. Basically, if you have a point, it's right here, and your camera was rotated by this amount or something, you can multiply by this matrix, and that point will get moved for you. Basically, that's what this math does. So let me just share just one little piece of OpenCV with you. So there's this function called Rodriguez. I'm not sure why it's called Rodriguez. I'd like to know. But if you plug in those Euler angles, the roll, the pitch, and the yaw, it will return to you a rotation matrix. Now, in our case, our camera, we've intentionally aligned our camera like directly with the coordinate frame. So the camera is pointing right at the origin. There's no rotation at all. It's rotation free, right? So it's not yawed relative to the origin. It's not pitched. None of that. It will be soon, but it's not right now. Any guesses? Does anyone in the class have a guess at what our omega values will be? So if I have no rotation, right? There's no rotation. The camera is pointing directly along the axis of the world coordinate system. There's no roll, no pitch, no yaw. Does anyone know what the omega, these 9 omega values? Any guesses what those 9 would be? So Ashish has part of the right answer. So they're not all ones. Remember, this is matrix math. So it's a good guess, Ashish. It's kind of the matrix equivalent of 1 of the unity operator. Any other guesses? What would our 3? This is like a 3x3 matrix. These omegas. Yeah, so diagonal ones, and the linear algebra word for that is the identity matrix. So yeah, it's an identity matrix. So it's just ones along the diagonal, right? So yeah, great, Nick, great, Jagadish. Cool. So if I plug in 0, 0, 0 into Rodriguez, I get out, there it is. There's the identity matrix. And let's start putting this together. So here we go. So I've taken, I hope what I've described to you reasonably well, and I've put it all together in our equation. So let's look together. So let me just ask the class again. So where did this come from? So these numbers right here, the 2003, the 1161, where did we get those 4 numbers from? What is this matrix called? Where did it come from, this first matrix? Yeah, it's the intrinsic matrix, right? Thank you very much. And where did we get it from? Where did I make up these numbers? Where did I get 2000? Where did I get 1161? Where did I get those numbers from? Sensor info, sure, but where did we actually get it? What process did we have to do to get this information? Because I didn't just read this off a spec sheet. I could have maybe, but not always. Here we did something a little better. We didn't just read this off the camera specs. What did we do last lecture to get these numbers? What process did we perform? We solved some equations, sure, but that process, so yeah, you're right, Jagadish, we solved equations, but that process is called camera calibration. That's what I wanted to get at here. So remember, we had all these checkerboards and stuff, right? We took pictures of these checkerboards, and that whole process at the end, it spit out the calibration, which was this. This is where I got it from. So this is the calibration that was computed by Zhang's algorithm. That gives us those intrinsic parameters. So I didn't just make these up, right? We computed them for my camera, for this the Panasonic GH4. Okay, so that's where those numbers came from. Now here are these numbers. Hopefully you recognize these, right? So here's that identity rotation matrix. So it's the identity again because the camera is directly facing the world coordinate system, the image plane, or not the image plane, the world plane that we've made. Remember, this is 0 and 0 because we have no offset in the U direction, no offset in the V direction, and then we have a 310 millimeter offset in the W direction. And there we go. So here is an equation, right? So this equation maps. It should map world coordinate points to image coordinate points. So let's press on here. Excuse me. So we're going to make a little bit of a simplification real quick. And it's going to be true for everything in this lecture. It's going to make life a little bit easier. It's very similar to how I was able to make that map of the road from that car. If you remember that, if we look back at this lecture, it was actually our first lecture in this module. So here, remember this cool map I made, right? I did it by assuming that the world was like a flat plane. And it's the same thing here, actually. It's kind of cool. So if we look at our setup here, right, we're taking a picture of a flat plane, right? And this is the origin of that plane. So for any point on this plane in world space, what would the W value be? So like we have different U and V values. Like this is a U value of 50 negative and a V value of negative 50. What would the W value be for a point on this plane? Any ideas? It's 0. Thank you, Pooja. Yeah, it's 0 because if it wasn't 0, it'd be off the plane. So the W direction measures displacement above or below the plane, and everything on the plane has a value of 0. So we're going to use that fact to make our math a little bit simpler here. So here's our equation, right? And notice that I've popped a little 0 in here, right? So see, I put a 0 in here for W. And if you think about how your matrix math is going to work, so I do row times column, right? And when I get to this third column, right, this is always going to be 0. So like it's going to be W13 times 0, W23 times 0, W33 times 0. So it turns out I can actually kind of cancel out this column because this 0 is going to nullify it. So I can simplify it and just lose that column. I hope that makes sense, so that this column gets to go away. Which is interesting. It means that that part of the rotation doesn't matter anymore because you're assuming all your points are along this plane. Okay. So this is our simplified equation here, and let's press on. Let's move forward, and I want to really solve this thing. So we're gonna solve it in Python. You know, I might do it on the whiteboard if we were in person, but it's a little bit of math, so we're gonna do it in Python. So here I'm setting up our world coordinates. Let me zoom in a little bit. Here they are. So remember at the beginning of this lecture, I showed you this figure, right? So we have point A, point B, point C, and point D, right? There they are. And I'm putting them into Python here for the first time. So here they are in Python. So here's like that point A was at 50, negative 50 for U and V. The W value is 0. And why have I added this 1 here, right? What is this? Why did I add this random 1 here? This is an idea we presented back last week in the first lecture of this series. What is this process called? This will be on your quiz. Why have I added a 1 to this vector? Faster computation, sure. It makes matrix multiplication happy, says Hernan. Sure. Those are both true. Well, faster computation, maybe. Depends. Matrix multiplication happy, yes. What is this called though? Match dimension, sure. What is this idea called though? There's a big hint on the screen. What is it called when we add this 1 on the end? Yeah, it's called homogeneous coordinates. So if I just had these first 3, this would be called Cartesian coordinates. And by appending this 1 to the end, I've converted to homogeneous coordinates. And that's the coordinate system we use in this module. For a few different reasons, it makes the equations linear. So those are our points. And now what I'm going to do is I've taken this equation, this extrinsic simplified equation here, and I just got this by, remember we decided to lose this column. So I just took this equation and I lost this column, and I get this equation here. And with plugging in the numbers, I get this. So here's that equation in NumPy. So 0, here's our identity, and we've got that 310 right there. And now I'm going to go ahead and do this matrix product. So I'm going to go ahead and multiply this matrix by this matrix. Remember that annoyingly in NumPy, if you want to do a matrix product, you call np.dot, which is very confusing because it's not a dot product, it's a matrix product. So that gives us this matrix we're going to call phi, which is the product of these two. And now all we're going to do, it's pretty cool. So for every point, so look at what I'm doing here carefully, right? So for every point, I'm taking phi, which is phi is this matrix times that matrix. And I'm just gonna do the math, right? So I'm gonna multiply this matrix times the vector. So I multiply phi times the vector, the matrix product. I'm leaving out that third value of the vector because that's the W value which we lost on purpose. And then the one last thing, just a reminder, let's talk about homogeneous coordinates. This will be on your quiz, so I want to make sure you feel good about it. Let's say I have some vector. Let's call it vector Cartesian, for example, vector Cartesian. And let's say it's the vector like 1, 2, 3 or something, like this, 1, 2, 3. Cool. And actually, I'm going to use a list just because lists are going to be a little friendlier. Okay. So there's our Cartesian vector 1, 2, 3. Oops. Control MB. Cool. Okay. What is this in homogeneous coordinates? So anyone throw it in the chat window, please. How do I convert this to homogeneous coordinates? What would this be in homogeneous coordinates? Any ideas? Can I spell homogeneous? That's a good question. OUS? Yeah, okay. Yeah, so 1, 2, 3, if I converted the vector 1, 2, 3 to homogeneous, what would it be? What is the homogeneous version of this Cartesian vector? So it's pretty simple. So all we have to do, like I said, this will be on your quiz on Monday, just put a 1 on the end. So just tack a 1 on the end, now you're in homogeneous coordinates. The one I really want to ask you about is if I give you a homogeneous vector, so be homogeneous, let's say it's like 1, 2, 3. Actually, let's make life a little easier on ourselves. Let's say it's 2, 4, 6, 2. There we go. Cool. Yeah, so Jagadish, you got that right. Good. Maybe there's a little bit of a delay. So yeah, Jagadish, you got that first one right. Good job. Now for homogeneous to Cartesian, so how do we do this, right? If this is the homogeneous vector, 2, 4, 6, 2, right? What would that be in Cartesian? How do we go the other way? Yeah, so we divide the whole thing by 2 is what we do. So yeah, thank you, Jagadish. Good job. So we divide this whole thing by 2, basically. So in Cartesian, we're going to lose that last value, but we divide the whole thing by 2. So it's actually 1, 2, 3. So in Cartesian, it's 1, 2, 3 because we divide the whole thing by 2 and we drop the last value. Let me give you one more just for fun. Let me give you 3, 6. Is that what I want? Maybe. Is that what I want? No, that's not what I want. Sorry, I want, no, I do want 3. I want 3, I want 6, and I want 9. Yeah, that's what I want. Cool. 3, 6, 9, 3. 3, 6, 9, 3. So yeah, Hernan asks, is the last value supposed to be 1? So no. So Hernan, great question. When you go from homogeneous to Cartesian, you lose the last value. You just take it off. You take it back off. So yeah, so it's just 1, 2, 3. Good question. What about this one? So if I have 3, 6, 9, 3, right? Yeah, divide by 3. What's the answer? Videhi or anyone? What is 3, 6, 9, 3 in Cartesian coordinates? Yeah, it's 1, 2, 3 again, right? Cool. Okay, great. All right, I hope that makes sense. That will be on your quiz. Okay. Speaking of quiz, Arvind and Rohan, I owe you some quiz solutions. I'll put that on my list.
Yeah.
All right, cool. All right. Okay, so that's just a little bit about that. The reason I bring this up, guys, is because we're about to do it in real life. There we go. Cool. All right. So here, I've done the dot product, right? Now that got us to here, but I have to go back to homogeneous coordinates. So to get the final point in the image, I divide by the last value. So image A, this is going to be a vector of length 3. It's homogeneous. I divide by the last value and I drop the last value, and that's how we get it in Cartesian coordinates. So here I'm actually doing this conversion. And we're about to visualize it, right? We're about to visualize the results. And as you can see, this went very well. We were supposed to get an error. No, I'm just kidding. Let's see. Now it works. Cool. Okay. So we're about to have a moment of truth. Before I show you the result, let's speculate for a second. So we just went through all this math. We had a point in world space that I very carefully measured using a measuring stick, a ruler. And if I've done my job right, when we get this result, which we've just computed, but we haven't looked at it yet. When we get this result, it's going to give us a point in image space, right? A point in image space. It's going to be pixel coordinates, right? So like it's going to be like, you know, in this world coordinate system. So if it was like, if the answer was 200, 200, it'd be like a point here or something. And our hope, if we've done all this, if we've done our homework, if we've done this correctly, then the point we get out for A should be very close to where A is in the image. And that might sound trivial, but it's really not, because remember, how did we figure out where A was in the image? Like we measured it in world space, we took a picture with a camera, we calibrated that camera to find all these numbers to multiply it by, we made some assumptions about rotation, translation, we did a bunch of stuff, right? So if this point actually ends up close to A, we should be pretty proud of ourselves, because we had to do a lot of measurement and math to get there, right? And what I'm really, this might seem trivial, but this is the thing, like this mapping between image and world space, like that's the thing in this module. So if we can really do it on simple examples like this, then it's going to be it's critical. That's the core of this module. So let's get into it. Let's have a look. So fingers crossed. How did we do? Let's visualize this production. I'll run this code. Here we go. 1, 2, 3. Boom. Okay. So here we go. So this is A calc. So we calculated A, it landed right there. This is B calc, this is C calc, and this is D calc. How did we do? Are you impressed? Are you underwhelmed? Is this, lame? What do you think? Did we do a good job? Did we not do a good job? How do you feel about our results? I agree. Jagadish says good job. Jagadish is in a good mood, maybe. Yep, I agree. Monica says good. All right, I'm pretty happy too. When I made this lecture 2 or 3 years ago, I guess 3 years ago, I was pretty happy, and it probably took a little tuning to get right. But I was like, yeah, it's not perfect, but hey, we measured with a measuring stick, we calibrated the camera, a bunch of stuff can break, right? So this is not bad. So there you go. So I hope that makes sense, and we're about to crank up the intensity. That was kind of level 1. We're going to go to level 3 shortly. But yeah, that we walked all the way through the mapping from world space to image space for 4 real points, and they landed close to where they should be. They landed close, and I've kind of like cheated. I'm not cheated, but I drew these points intentionally on a grid in the image to show you, where they're supposed to be, and we're kind of lining that up to see if they actually are. So that's that. And now, how am I going to increase the difficulty, right? What am I going to do to you? How am I going to make your life harder? So here's what I'm going to do to you next. The camera is still directly overhead. It's still directly overhead, but what I've done, as you can see, is I've rotated I've rotated the camera by 45 degrees by √2/2 radians. I've rotated the camera. So let's see how this changes our math. Can our math handle this? I hope so. Let's find out. So here's our equation again, right? And I want you to start thinking about what's going to change, right? So let's think together carefully. We're still able to use the simplified equation because our points are all still on a plane, right? They're still on a plane, so there's no, the tau3 or the W value, excuse me, is 0. So we have our simplified equation where we've lost that column, and we have no W value. Help me start thinking about these variables though. So these are going to stay the same. I hope that makes sense. These are just results of camera calibration. But these are going to change because the position of our camera has changed. But not all of them are going to change. So help me think through this now. Tau1. Do you think Tau1 will change? Here's the image, right? Here's the image. And remember, in the original, Tau1 was 0. Tau1, and that's the displacement of the camera relative to the world coordinate frame in the left and right direction. Will this change? Well, what will Tau1 be? Any guesses? Guesses for Tau1 in this, and that's the U direction, the left and right direction. Any guesses for what Tau1 will be? And all I've done is I've rotated. Yep, thank you, Jagadish. So the camera has not translated left or right, it's only rotated. So Tau1 is 0, good. What about Tau2? Any guesses for Tau2? Thank you, Nick. Yep, cool, all right, 0. The camera has not moved this way, right? Okay, good. And then finally, Tau3, any guesses for Tau3? What will our Tau3 value be? Yeah, I think you mean 310, but yeah, so yeah, it's that 300 value. Yes, thank you, Hernan. Cool, so those are actually identical, nothing has changed, right? So if the taus are the same, what changes? What's gonna be different about our equation then? Taus are the same, what will change? Yeah, the omegas, thank you, Nick, yep. So these omegas will change, perfect. Okay, so how do we find the new omegas? Again, we're going to use this Rodriguez function, and this computes a rotation matrix from the pitch, the yaw, and the roll of the camera. Here, I haven't done any pitching. I haven't moved the camera this way. I have not done any yawing. I haven't done this, but I have done this. I've done roll. Right? I rolled the camera, just like an airplane would roll, right? So I rolled the camera. It turns out the roll is the third input to the Rodriguez function. So notice I've passed in pi/4, which is the, did I say √2/2? I'm sorry, earlier. 45 degrees is pi/4 radians, not √2/2. That's the ratio you get for the triangle when you, anyway, so in radians, 45 degrees is pi/4, so I plug this in. I get back this answer, which might look a little familiar. You get 0.707, that is √2/2. There's other ways to set up this equation if you want. You can just use Rodriguez, but it turns out that 2D rotation, a 2D rotation matrix ends up looking like this. You have sines and cosines. If you plug those in, you get the same thing. I just wanted to show you that. Feel free to review that. I won't quiz you on it or anything. All you really need to know is that there's a function called Rodriguez. Plug it in there, and it will spit out the rotation matrix for you. So here it is, and I went ahead and put these in square root form just to make our math a little bit prettier. So here it is. So this should look very similar to our last equation, right? But the only thing that's different is that this used to be like the identity matrix, kind of. And now it's this root 2 minus root 2, root 2, root 2 kind of thing, which we got by plugging in our 45-degree rotation. So we're going to solve it again, and we're going to cross our fingers, and we're going to hope that our points line up again, right? That's what we hope. So let's try it. Let's hop into it. So I'm going to plug this in. Here's our extrinsic simplified. I'm using the cosines and sines that I mentioned. I'm not actually using the Rodriguez thing, but you certainly can. It'll be the same result. And then I'm going to plot it. So let's have a look. Let's see. How do we do? Here we go. So let's have a look. So boom. So that's not terrible, right? So these things are still roughly in the right place. I forgot how I actually measured 45. I think I have a protractor in my office, and I must have used a protractor, like I was in geometry class. But here you go. So this is not bad. So again, A is close to A, B is close to B, C is close to C, and D. Actually, are these off by one? That's really funny. I didn't notice this last year. Look, A is next to D, and I wonder if I have the direction wrong. That's fascinating. If I plugged in negative 45, would that fix this? This is a little bit of a diversion. No one has ever pointed this out to me in my notes, which is interesting. Interesting. Ooh, if I plug in a negative here, is this going to fix it? Let's see. No one has. Oh, it did. I had the wrong rotation direction. That's pretty funny. Okay. All right. Yeah. How have we not caught that? That's interesting. Okay. So notice what I did here. So before this was positive 45 degrees, and if I plug in positive 45, it's rotated 45 in the wrong direction. It should have gone this way, but it went this way. So see how A is close to D? I didn't notice last year because it kind of looks right, but the letters are off by 1. So I'm 90 degrees off basically, right? And just for fun, like what if we had done pi over 8, for example? If we only rotated by pi over 8, where do our points end up? They should be like, yeah, see, they're like halfway there, right? So that's cool. So what it should be is negative pi over 4. I got to make sure I push that fix, or maybe I'll keep it as an Easter egg. Anyway, there we go. So this is correct. So I had the wrong direction. Okay, so that's pretty good. Our math is holding up pretty well, I would say. So now I'm really going to get crazy. Before I do get crazy, let me show you one more thing. So all of this mapping we're doing, at the end of this lecture, I'm going to kind of summarize all this together for you. And I'm going to say, hey, here are the big classes of transformations from plane to plane. Because what I would like to emphasize right now, everything we've done is mapping from one plane to another plane. It's like a transformation from plane to plane. What are those two planes? In this case, remember, I set up a plane at the beginning. I set up this plane, this world coordinate plane. This is a plane. And the other plane is the image sensor, right? So there's some mathematics that describes the mapping of a ray of light from a point on the plane into the image sensor of the camera, or onto the image sensor. And that's what this math does, right? So it's a plane-to-plane mapping. It turns out there are different varieties of plane-to-plane mappings, and the ones we've been doing so far are what are called similarity transformations. So this is a figure from Prince's computer vision book, and here the red is the original, and under a similarity transformation, the red can become any blue rectangle or any blue square. So basically, the aspect is preserved, so it remains a square, but it can be rotated and it can be scaled. This transformation in general, this model of transformation, has 3 degrees of freedom. It has a scaling factor, a rotation, actually 4 degrees of freedom, rotation factor, and then it has 2 translation. It can be moved up, down, left, right. We're about to get into a more sophisticated translation model, but I wanted to stop here and show this one to you. So both of these examples we've done so far, when this square gets mapped to the image space, it has been scaled, rotated, and it could be translated up or down, left or right. That's what's happened so far. But it's about to get more serious. This assumption that a square remains a square is about to be broken. And I'm going to do that by moving the camera again, but I'm going to move it in a different way. So let's see it. So here is where stuff gets real. So let's have a look. So look at this angle, right? So here's the same square, but it's at a different angle, right? When these points get mapped to image space, the thing I want you to think about in your brain for a second is, are they still a square? Do they still represent a square in image space? It might be kind of hard to see, but they actually don't. It turns out to be it's actually it's a parallelogram, I believe. So yeah, because of the angle the camera's at, squares are no longer squares, which is kind of interesting, right? So can our math hold up to this, right, is what we're about to get into. Now, there's kind of two options here, basically. One option is I could try to estimate all these parameters with you. I could say, okay, I must have moved the camera down this far at like an angle of 30 degrees, and maybe it's at this angle to the side. We could do all that. In practice, that's pretty hard. That's not what we're going to do here. We're going to actually solve for the location of the camera because we actually know where these points are in the image. So let me show you how that works. It's pretty cool. So here's our equation again. Same model applies. But we're going to use this method called solve P&P that's built into to OpenCV. And just to let you know, this is going to be a different kind of mapping because a square is no longer a square. So this type of mapping is called a homography. And a homography is it's the most general type of transformation from planes to planes. So any kind of angle your camera can be at relative to any kind of other plane, that mapping can always be described by a homography. And we'll get into the different transformations, all of them together at the end. But this is more complicated than the similarity transform because it can represent transformations that make squares no longer squares. So that's the idea here. Yeah, so great question. So Jagadish is kind of asking, like, can we train a neural network to do this kind of thing? You certainly could. Here we don't really need it. So the models we have are pretty good. Now, I shouldn't say that. So in many cases, you don't need it. But for more complicated applications where you need a lot of precision, yeah, training a neural network could be pretty cool. Before you would do that, you'd probably want to look at the next level of sophistication of camera models. So here we're using some of the simpler camera models. There are fancier camera models, and those may do better than a neural network. But there's no reason you couldn't learn this transformation. That's totally reasonable. I'm sure someone has tried it, and I think it could work well. You may have a challenge with different cameras. You'd have to train it for every different camera, but it's the same idea as calibrating. You know, every camera would have to be calibrated as well. So that's a great question. Okay. So we're going to use this find homography thing basically, and what that's going to do, it's going to compute the mapping for us basically is the idea. And there's several ways you could do this, but what we need to do next is we need to actually find the pixel coordinates of these points to plug into our equation. So we need to figure out what pixel location this is. To me, it looks like it's at about 400, 1400 maybe, something like that, but I want to be more precise. So to do that, there's a bunch of ways you can do it. You could just open that image in like a viewer or something. One option is the QT option, which I just wanted to mention here because we haven't really talked about it in this class. So in this class, we're using inline, this PyLab inline thing where all of our plots are in the notebook. But it turns out you can actually have these plots pop out of the notebook if you want. And I think my screen share is going to fail us. Yeah, hold on, let me switch screens. So I just ran that code. And it popped up a new screen, but you can't see it because I'm not sharing it. So just give me 1 minute here and I'll share that screen. So here it is. Yeah, so this popped up for me, right? And just by doing that PyLab QT option in the notebook. So here's the same picture, but what's great about this picture, right? Notice when I move my mouse around, on the bottom left, it gives me coordinates, right? So if I put my mouse right there, it tells me the coordinates of that point. And I can also zoom and stuff, right? So you can't zoom really in the there are ways you can do it, but in the standard in-lab figure in the notebook, you can't zoom. But here you can zoom, and I can put my mouse right there, and I can say, okay, that point is at 12. If you can't see, just look in this bottom left corner. That point is at 1286, 337. So the idea is we record those values, and let me switch my screen share back to lecture. So we record those values. Here they are. So here's the 4 points I picked off from the image using that PyQt thing. I'm going to put the notebook back in inline mode. I think we'll need it to be in inline mode in a second. And I'm going to comment this out for now. Okay, so there's those points. Oh, I did the same thing here. That's funny. Okay, so what we're going to do then is we're going to solve this find homography thing. And that's going to it's going to compute the transformation matrix for us. So like, remember how when we put all this together, like, I think the best example is up here. Actually, no, it's probably right here. Yeah, like here. Remember that when we did the math in Python, we multiplied these two matrices together into a 3x3 matrix called phi. So right here it is. So we multiplied, you know, we did this matrix times this matrix to make this phi matrix, right? So when we do this find homography thing, it's going to take the pixel coordinates we give it and the world coordinates we give it, and it's going to return an estimate of that phi matrix for us. Now, it's not so powerful that it can actually compute the intrinsics and the extrinsics for us, but it can compute their product. It can compute phi, basically, that phi matrix. So I'm going to run this to find that phi matrix, and I'm going to run the same math to project the image points or the world points to image space, and I'm going to plot them, and they're going to line up really well. But you shouldn't be impressed by this, because we basically told the algorithm, we told it where those points were, and we had it solve for phi. But I do want to show you something that I hope you're impressed by. This should not be very impressive, but I want to show you one more thing. So what's really cool is once we have this homography matrix, so we just computed this homography matrix phi by telling it what a pair of four corresponding points. We said, hey, for these 4 points, you know, here's the location in the world, and here's the location in the image. Please find the mapping, and it found the mapping for us. Now that we have this mapping, now that we have phi, and let's just look at phi together really fast, just for fun. Oops, there we go. So phi, yeah, so here it is. We have this mapping matrix. Now that we have it, we can do something really, really cool. We can use this to actually warp this image to make it appear like we're looking at it from a different angle. So there's a function in OpenCV called warp perspective. And we can use warp perspective to simulate or to transform the image into what we believe it would look like had we been at a different vantage point. And this won't work for general 3D problems, but it works for planar problems like this, which is all you need in some applications. So let me show you. So to do this, we take the inverse of our phi matrix, basically, and then we're basically going to use this warp perspective method. So there's a little bit of math going on. I won't spend too much time on it, but we're going to adjust this matrix to make it appear, or we're going to adjust the image using warp perspective to make it appear like our camera was actually directly above. We're going to synthetically move our camera because we know the mapping now. So let me show you that. So here it is. So here is that same exact image. So it's the same image, not a new image, same image, but I have warped it to make it look like the camera was overhead. So maybe that's impressive, maybe it's not. I think it's really freaking cool. Let me show you again. You know, this is the original image, right? And we warped it because we know the mapping. And you could simulate other angles too. You could simulate off to the side, whatever you want. It's really, really cool, right? And this is commonly used in areas like autonomous driving to make what's called a bird's eye view. You can take a view looking at a road and you can warp it to make it be the overhead view. So that's pretty cool, right? And again, it's not using machine learning. It's just using that camera model, right? It's just linear algebra, 3 or 4 variables, that kind of thing. So I hope that makes sense. It's very useful. I just want to preface it by saying this only works for homographies. If you have like a general 3-dimensional shape, right? Like anything 3-dimensional, you can't do it this cleanly. There's stuff you can do, but that's really like the OpenSFM kind of stuff you're going to do for your challenge. But for planes, this works really well, right? So it's the same image, and you can actually tell that it's been warped. See how this is kind of fuzzy, right? It's because look how few pixels were captured. So if you look at the original image here, right? See how this is kind of like fuzzy and kind of a little out of focus and stuff, right? You can totally tell. So look at this, right? It's still fuzzy in the final, because of course it is, because it's the same pixels. They've just been warped to a new perspective. So it's still fuzzy, but it looks weird that, see how this is very in focus, but this is out of focus? It doesn't make sense from this view, right? But it totally makes sense from this view, because the camera, this is further away, so it's a little out of focus, and this is more in focus, right? And here it makes sense. That one's really in focus. That one's kind of out. But that sticks around, of course, because it's the same image. It's just been warped, right? It's just been warped by this warping operation. Okay, so that's homographies. I promised that I would tie all this together, so here it is. Here's a great figure from Selinsky's book. Yeah, so does warping quality depend on the resolution? Yeah, totally, right? So a low resolution image will not look as good. For sure. Yeah, good question. Okay, so these are the different plane mapping. So if you're going from plane to plane, these are the 5 different kinds of mapping I would like you to know about. I won't quiz you on all of them, but it's good to know that depending on the kind of computer vision problem you're solving, you could be looking at one of 5 different kinds of mappings. The simplest mapping is just called a translation. That's where you take a square, whatever shape you have, and you just move it around. This is not quite sufficient for the kind of problems we solve usually because we have to scale the image as well. The next option is called a Euclidean transformation. That's where we do translation plus rotation. So there's 3 variables now we can translate or rotate. And actually, hopefully this math makes sense to you guys. So this is the same matrix we've been talking about. So I stands for the identity matrix. And if you're translating, then your big extrinsic matrix has tau, which is your tau 1, tau 2, tau 3. Actually, sorry, just tau 1 and tau 2 in this case. But then this is the identity matrix, basically. So this is like the extrinsic matrix altogether. And that little vertical line, that's saying that it's like a matrix and a vector put together into a big matrix. Okay, so then you have similarity. So in similarity transformations, you can scale, you can rotate, you can shift left and shift right, shift up and shift down. It has 4 degrees of freedom. It preserves angles. The next level, we kind of skipped over the last level, but it's an important class of transformations called affine transformations. So in affine transformations, the parallelism is preserved, basically. So actually, I misspoke earlier. So I said that the squares were becoming parallelograms. They're actually becoming trapezoids, and in some cases, just quadrilaterals, actually. Just there's no preservation of angles. But with an affine transformation, which we skipped over, but there are certain types of problems in computer vision where we would have an affine transformation. There you would have parallelism preserved, and there's 6 degrees of freedom. And then finally, in a projective transformation, which is the same thing as a homography, there are 8 degrees of freedom, and this is the final kind of mapping we did. So this mapping here, this was a homography, and there are only straight lines are preserved. Notice that in the image, even though this is not a square anymore, the lines are still straight, right? So imagine a transformation that didn't preserve straight lines. That'd be pretty crazy, right? But thankfully, projective geometry and vision, for the most part, except for camera distortion, preserve straight lines. And that's this final class of transformation. So that's a little bit about transformations. I'd say don't worry about the details of this too much. I would like you to know about homogeneous coordinates. I'd like you to know a little bit about, really the thing that I really want you to know about is I just want you to have some level of comfort with this equation. Like, that's my big hope for you in this module, is that if you see this equation in the wild or you need it for something, I don't want it to scare you. Like, that's my main thing. And I hope going through this lecture makes this equation less scary. We walked through all the numbers. We solved it 3 times. I hope that all makes sense. Please feel free to review. I'll ask you on the quiz some very basic questions about this equation. I won't ask you to solve a crazy version, but I may ask you to solve a simple version. But this really is the equation. That's my hope for you. I'm not too worried that you know the difference between an affine transformation and a homography. What I do want, though, is I want you to feel comfortable with this equation. That's really my goal. Okay, so we have 12 minutes left of my lecture for the year. That's pretty crazy. If there's any questions about transformation, please throw them in the chat window. We have a little bit more to cover. We have a little bit of what's called ransack. But before I do that, I just wanted to pause for a second. I was going to pause earlier, but we got into the transformation lecture. And that's really the main meat for today. We'll spend a little bit of time on ransack, but that's really about it. I just want to open it up real quick, though. So we've got 24 people today. Attendance trails off at the end of the semester. I found that to be pretty true unless you require students to come to class, and it makes sense. People travel and get busy and stuff like that. But with the students who are here, you're going to do your course evaluations. Have those gone out yet, Arvind and Rohan? Of course, I think it's after the end of the semester. Is that right? The course evaluations?
Yes,
I guess they are out, Professor.
Oh, they're out. Okay. Have they been returned? Are they due already, or they're just out for completion?
They are due.
Oh, they've already been done. Okay, never mind.
They're not done. Sorry.
Oh, okay.
So they're not done.
Okay, good. All I was gonna say is, do please take those seriously. Those do have an impact on Rohan, Arvind, and I. So when our bosses or whenever we're up for the next position or anything like that has a look. So those course evaluations do get looked at and they do get used, and we take your feedback seriously. So last year, we had some positive and negative here and there feedback, and we do take it seriously and roll it into the course. So please take time to do that course evaluation. It does reflect back on us. So we appreciate your time doing it. Just while we're here, it's our last kind of lecture together. We'll have a guest lecture on Tuesday, and then we'll have the project presentation. But I'll just open it up just for a second maybe just for a couple minutes before we go back into the ransack lecture. Any comments on the course, right? So we don't have a lot of chance for face-to-face and no chance for face-to-face interaction. So yeah, I'd love to open it up just a little bit. Anything you liked or did not like about the course, right? So you're almost done, right? You've just got a week left, something like that. And this course has just flown by, and doing it online there's been some challenges, right? So I hope it's been, I think it's difficult to compare to in person, but I hope that you've learned some stuff and that it's been stuff that you find interesting and useful in your career or whatever you end up doing next. But yeah, any comments on the course in general? Anything you've liked, haven't liked? Any thoughts? Yeah, so you wish it was a face-to-face class. Yep, totally. I agree. Face-to-face it's just more fun, absolutely. So Siddharth says he learned a lot, but would love to have it been offline. Yep, I totally agree. So Hernan liked the insight from the industry and the guest speakers. Awesome, good, that's great. We had an interesting collection of guest speakers this year. They covered a pretty broad range. So Monica says she's not scared by CV. Good, that's awesome. Yeah, it's not that crazy. Like it's a big field, right? But no, there's nothing. I'm glad. That's really good news. Any other comments, right? I mean, there's a bunch of ways to do an online class. Rohan may be a TA. We'll see, but he might be TAing for the same class in the spring. Do you guys? Is there anything we could do better for the online class? Right? Any thoughts? The video format's okay. You guys remember the very first lecture when it took me like 10 minutes to set up my screen and stuff, and that was so terrible. Do you guys have any comments? Like, is there anything we can do better, right, that will make the online more livable? Yeah, so Ravina says she loves it. She learned a lot, and the interaction made it more interesting. I agree. Yeah, yeah. So Baraj, yeah, okay, cool. You said that VW, perfect, thank you, that helps me a lot. You said you wish it was offline, totally. So Jagadish liked the polls. We didn't do as many polls towards the end of the class. I wish we had done more and kind of kept those up a little bit better. But yeah, is there anything else we could do better? I'm not teaching next semester, but pick the highest score in Auto Lab. I really like, I think Pooja's on today. Pooja, that was really awesome when you shared your solution. That was really cool. I think I'd like to do more of that. That was pretty neat. More help would be nice, says Hernan. I don't know. I've never had a grad class before. Sure. Yeah, totally. Yeah, that was awesome, Pooja, right? I think I'd like to do more of that in the future, right? More of the having students share their solutions. That was really, really cool. We only did it for one challenge, right? I wish we did it more. Is there anything else that we can do to help? The course is pretty much over, but I'm kind of trying to get feedback for future years. And I don't know if I'll teach another remote class, but I could. And I know that Rohan may be TAing next semester for an online class possibly. So do you have any other thoughts? Anything else we can do that could make online less painful? Okay, yeah, so BW likes the quizzes. Okay, good. I'm glad the quizzes, yeah, hopefully those quizzes weren't too stressful. Do most online classes, are most people still doing exams and stuff, like exams over Canvas? Is that how most people are still doing? Yeah, okay, yeah, that sounds okay, cool. I don't know how we would do that. That's interesting. Right. Okay. All right, well, I don't see anything too direct. Yeah, the online thing is just tough, right? And I do think that it's way nicer to have some interaction. Even today when the class is kind of small, like it's way nicer to have some back and forth than just like no back and forth, right? So I really appreciate it. The one lecture that I just straight recorded, it was terrible. I was so bored, and like actually I cut it short because I was just like, oh, I hate this. So some courses have exams on lockdown browser. Yeah, right. Yeah. Cool. So Monica thought the class was very interesting. I'm glad you thought it was well organized. I felt a little less organized myself this year, but that's mostly, so the reason that you thought it was organized is because Arvind and Rohan are doing their jobs really well. So that's good. I was not organized this year, but Rohan and Arvind were. So that's good. Yeah, so the last bit feels a little awkward. Yeah, so Abhijit, I totally agree. Like, I don't know where to put this 3D module, right? Because it only like, I guess we could cut it. We cut it last year. We just cut it. But it does come up, and like I'd say we have 2 or 3 groups this year doing 3D stuff. So it is important, but I don't know where to put it because I don't want to put deep learning way at the end, So maybe we try the crazy thing and do deep learning first sometimes. We'll see. So Videhi likes the projects being done with industry partners. Yeah, we like that too. Yeah, totally. So yeah, Hernan says, is there a mix of deep learning and 3D stuff? Yes, there is a mix. I'm trying to think of a good paper I can show you. I don't have a paper I can show you right away. If you look at the state of the art challenge, so if you're looking to get any extra credit, yeah, Hernan, maybe I'll share with you afterwards. But there is some 3D stuff. Plus, if you look at the state of the art challenge, which is the extra credit problem, actually I can get to it real quick, and then I'll look at Monica's question. Let me show you real quick, Hernan. So if you're looking at the extra credit challenge, if you go to, that's going to be under Intro to Computer Vision. And if you look at the challenge, this is basically like running, oops, sorry, this is the wrong one, not intro. I thought it was intro.
I guess it's in the intersection.
Oh, it is in the intro. Okay, why did I not see it then?
You just have to scroll down, I guess.
Oh, it's down here. Thank you, Arvin. I appreciate that. Thanks so much. So yeah, Hernan, to answer your question, I think, yeah, if you look at human pose estimation, for example, that's still 2D though, actually. There was at least one, yeah. So Hernan, if you check out depth estimation, this uses deep learning to estimate depth from images, for example. And then there was one other, I thought that we did like 3D kind of stuff. Maybe not though. There is stuff out there, but the only one that's in here is actually, it's this paper, which is depth estimation from monocular, basically. Yeah, cool. All right, cool. So let me catch up on these questions. Yeah, this is pretty cool. So take an image, not just one camera image, and estimate the depth from that image is kind of the task here, using deep learning. So Monica says, I guess you can take a class on CI/CD from a CV point of view. Yeah, so Monica, I totally agree. I would love to cover some like deployment stuff. I would almost take this class and just swap out the 3D stuff for deployment. Like that'd be pretty interesting. I'm on the fence. So the 3D stuff, like I said, I do think it's important. Maybe it'd be cool one year to have like a choose your own module at the end where like there's like 5 different options you can pick from. I don't know how we would do the lectures, but maybe that'd be kind of cool. You could kind of pick what area you wanted to specialize in. Cool. Yeah, so Videhi says more production models would be good. Yeah, I agree. You know, and honestly, that kind of mirrors my own career. And I think kind of where the industry is going is like now the thing that kind of sets apart a professional, experienced data scientist is like the ability to deploy and maintain this stuff, not just the ability to train the model. So yeah, that could be a whole course, honestly, but maybe it could be a module. That's a great point. Yeah, really good point. Arvind and Rohan, any comments from you guys? Anything you do differently, you know, just while we're kind of wrapping up the class, right? Any thoughts or comments?
Oh, we discussed these at the beginning of the lecture, actually.
Oh, you were already talking about it. Okay, cool. Anything you care to, anything you can share here? It's okay if you want to talk offline, but
No, I guess we did organize the lecture and the course pretty well.
yeah, you guys did a great job. Yeah, absolutely. And just so you guys know, the students who are on right now, I've been really busy at work this semester. Like I usually in the past, I've taught for 3 years, and the first 2 I just had more time. So Arvind and Rohan have really, really stepped up. So make sure you thank them because they really keep the course running. Without them, they would just be a cluster F. It'd be really disorganized. Yeah,
so not just that, Professor, I was talking about the course and the complete course material that you have arranged. And that was
okay.
really done pretty well.
Oh, that's good. That's good to hear. Great. I'm glad you like the order. When I made this class, I had a little more free time. And yeah, that's good to hear. Oh yeah, we barely got to do GANs. So yeah, Aparajita is saying, hey, can we do GANs? Yeah, that'd be cool, right? We like barely. You can go look at the lecture on that, but yeah, we only had like 20 or 30 minutes for GANs the whole year, which is kind of depressing. They're super cool. I have like a little interactive module thing on GANs that we didn't get quite to, but where you can like synthetically age faces. I think we did that last year, right? Rohan and Arvind, we did like the face aging with GANs.
Yes, Professor.
Yeah, we skipped that this year, which sucks. Yeah, I wish we had time to cover that. But yeah, absolutely. And then maybe just, I guess it's 3:45, so feel free to drop if you need to. I just want to look at one more thing together, and I should have pulled this up at the beginning. And Arvind and Rohan, feel free to hop in with any other comments you have. The one thing, let's see. Yeah, this is what I look at. So I don't know if you guys remember the very first lecture. These were my goals for you, basically, right? Like this is what we wanted to do in this class. So you know, if the class has been successful, you've done these 8 things basically. So like the things we set out to do together were to set up and manage a scientific computing environment. If you've made it this far, you've pretty much had to do that. Implement key computer vision algorithms in Python to solve real problems. Train and validate machine learning models to find database solutions to computer vision problems. Interpret algorithm performance through measurement techniques and visualizations. Debug problems. If you've made it through the challenges, you've definitely done some debug. Understand the difference between analytical and empirical. So I hope that for anyone in the class, if someone asks you the difference, you can explain this now. Discuss the historical trends in computer vision and research developments, and then collaborate with your peers and advisors. So I hope you feel like you've gotten these 8 things out of the course, even though it was online. You know, these are the big things that I really hope that kind of came through. But yeah, I really appreciate your involvement in playing along, you know, with the online thing. Like I said, it definitely has been, it's been tough. It's just, I think it's harder for everyone. I think everyone's tired. Maybe the last thing I'll say is just that please have a nice break. You know, I know some folks have more school to do. You might have some more semesters of school. Maybe you're off to grad school next. Maybe you're looking for a job. I know a lot of people are looking for jobs right now. And yeah, please just give yourself some rest. It's been a long year. I think we're all tired. I think the whole world is tired. I'm definitely tired. And I hope that the holidays are nice and restful. And as a student, you know, these transitions can be really stressful. Like I remember when I finished undergrad, for example, it was really stressful to like figure out what I wanted to do next. You know, like did I want to go to grad school? Did I want to get a job? Where did I want to work? It's a lot of pressure, right? And nothing I can say right now is going to make you like calm and zen about it. But I'll just say that when I look back now, that was like 10 or 12 years ago for me. Like there was no way to make the perfect decision, and you know I just did my best and kind of muddled through, and it turned out fine, right? I guess what I'm trying to say is that you don't have to make the perfect decision. Like your career is going to be okay. You will find a job. Like things will work out. I promise. It's a weird time. Actually, when I graduated from undergraduate, it was the beginning of the last recession, right? So the financial crisis. So it was kind of a crazy time too. I think this time is crazier, but it was still pretty crazy. Like you had a really big unemployment, all kinds of problems. So got some background. So yeah, that's all I would say to you. I hope you have a really restful break. You know, I hope it's been a good semester. I know there's been a lot going on, and I think we're all tired. But I really hope you have a restful break. And the one other thing I'll say that I kind of wish I had told myself when I was kind of finishing school and figuring out what was next is, like now, like I'm sure this will be true for many of you. You're going to go off and do jobs or do research or do PhDs or all this good stuff. There will be times when you have no time left. So when you're a student. One thing that's just so nice is to have like, you know, 2 or 3 or 4 weeks off for like the holidays, things like that. So please just enjoy it. I know it's stressful because you're figuring out what you're going to do, but I wish I had taken more time just to relax and enjoy my time off, because now I have, you know, it's crazy how little time I have. And that's just how a lot of careers go, right? As you kind of work up in your career, you're going to get busier and busier, and time is going to become really, really, really precious, right? So yeah, I hope that you have a restful holiday. Please enjoy the time you have off. That's the advice I'd give to myself if I was in your shoes. And I know it's stressful to look for jobs and stuff like that, but do hang in there. I'm confident you guys can all be and will be successful. Okay, great. All right, good deal. So we've got a few comments coming in. Awesome, great. So yeah, I'm gonna go ahead and end it there. Thank you for your time today, guys. We'll see you on Tuesday just for a little guest lecture. And do get your last assignments done. Reach out to us if there's any questions or anything like that. But I'll go ahead and sign off. I'll turn off my video and stuff, and then I'll kind of catch up on these chats. So thanks, guys. Have a good afternoon.